So we just looked at finding concavity looking at a graph, but what if we're not given the graph? What if we're given the equation? So to find where your graph is concave up and concave down, first thing you want to do, so concavity, finding concavity. We want to find the second derivative. So we need to find the second derivative of x. We also want to find when the second derivative of x is equal to 0, or where the second derivative of x is undefined. And these are places where it could change concavity. And so these are possible inflection points. So once you find those values, when it's set equal to 0 or undefined, this is where I normally again do my number line. So place the numbers found. In my case, step 2 on the number line. And then you want to test intervals on the left and right. Of these numbers. Into the second derivative. If you find that you plug in a number and it was greater than 0, you know that it is concave up on that interval. You find if you plug in a number in that interval and it's less than 0, into the second derivative, it's concave down. On that interval. If it's defined at that critical number in our original function, where it was equal to 0, then that's where it's changing concavity, and that's an inflection point. So to find inflection points, you're going to plug that value of x back into the original function. So to find inflection points, plug the value of x where it is changing concavity. Back into the original function. Again, that's only if it's defined back in the original function. If it's not defined back in the original function, it's possibly there's a vertical asymptote there. Possible, not necessary. Okay, so let's look at one example and then we'll take a break. Let me pull out one of the easier ones. Okay, so it says find the open intervals where the function are concave upward or concave downward. Find the inflection points. And so let's say we're given that f of x is equal to negative x cubed minus 12x squared minus 45x plus 2. Okay. So we want to find out where it's concave up, concave down. If it is, what intervals? So we need to find the first derivative first. So f prime of x, so derivative of negative x cubed is negative 3x squared. Derivative of negative 12x squared, that gives us minus 24x. And the derivative of negative 45x is minus 45. And the derivative of the constant is 0. So now we want to find the second derivative. So taking the derivative of negative 3x squared, we get minus 6x. Derivative of negative 24x is minus 24. And the derivative of negative 45, a constant, is 0. So we need to find when is the double derivative equal to 0 or and undefined. Well, we have a line. A line is always defined. So there's no place where our function double derivative is undefined. But there is a place where that double derivative equals 0. So we're looking at when is negative 6x minus 24 equal to 0. So let's solve for x. We're adding x to both sides. So we have negative 6x equals 24. Divide both sides by negative 6, we get x is negative 4. So here's a critical number, possible inflection point, changing at negative 4. So we want to test a number to the left of negative 4 and to the right of negative 4. And we're plugging it in again to that second derivative. So choose a number to the left of negative 4. So how about x is negative 5? So if we play that into the second derivative, just like when we were finding where it was increasing and decreasing, we were just kind of worried about the sign. We weren't really worried about what number we got back. Same sort of idea here. If I take negative 6, multiply it by negative 5, and then subtract 24, is that number going to be positive or negative? I noticed that, well, negative 6 times negative 5 is positive 30. That's bigger than negative 24. So this is a positive number. So positive, it holds, the bowl holds. So this would be concave upwards. So choose a number to the right of negative 4. Plug it back into the second derivative and see if it's positive or negative. Well, 0 falls in that interval. 0 is bigger than negative 4. If we plug it into the second derivative, we get negative 6 times 0 minus 24. Which is negative 24, which is a negative number. So that tells me it's concave downwards. So concave up from negative infinity to negative 4. And concave down from negative 4 to infinity. Our inflection point, we know it's occurring when x is negative 4, but we need to plug it back into the original. So we need to look at what is f of 4. So that would be negative 4 cubed minus 12 times 4 squared minus 45 all times negative 4 plus 2. So I know if I cube negative 4, I get negative 64 with a negative out front. So this is going to be equal to 64. Negative 4 quantity squared is 16. 16 times the negative 12. So it's going to be minus 192. Negative 4 times 45, negative 45. That gives me plus 180. Plus 2. If I did this right, 64 minus 192 plus 180 plus 2 gives us back 54. So our inflection point was x was negative 4, our y value is 54. So pretty similar to finding where our function was increasing and decreasing. We just had to, instead of looking at the first derivative, finding when those are 0 or undefined, we're looking at the second derivative and finding where those are 0 undefined. And then we're plugging them back, checking intervals and plugging it back into the second derivative. We're increasing, decreasing, we're plugging it back into the first. So looking at another example for finding concavity where the function is concave up and concave down and inflection points if they exist. This function is a rational function. F of x is equal to negative 2, and that's all over the quantity x plus 1. So to find concavity, we want to find the second derivative. So first thing we have to do is find the first derivative. And looking at this, I need to use the quotient rule. Unless I want to rewrite it. But let's use the quotient rule. So that says we're looking at the derivative of our numerator, but the derivative of a constant is 0. So I have 0 times my denominator, x plus 1, minus my numerator. In this case, that was negative 2, all times the derivative of my denominator. So derivative of x plus 1 is 1, and this is all over the denominator x plus 1 quantity squared. So cleaning this up a little bit, 0 times anything is 0. And then we have minus and negative 2 times 1. So that's just going to be a positive 2 all over x plus 1 quantity squared. Okay, so that's our first derivative. Now we want to find our second derivative. So looking at the second derivative, using the quotient rule, looking at the derivative of my numerator, which in this case is a constant, 2, that is 0, all times my denominator, well, x plus 1 quantity squared, minus my numerator, which is 2. So now when I look at the derivative of the denominator, I need to apply the chain rule. So our outer function is this quantity square. So the derivative of the outer, so bringing down the power, 2 times of the inner, so keep it the same, x plus 1. Subtract 1 from our power, we just get 1, all times that derivative of the inside. And the derivative of the inside, x plus 1, derivative of the x is 1. And then this is all over x plus 1 quantity squared, but now that's squared. So cleaning it up a little bit. in our numerator, we're left with -2 times 2, which is -4, all times that quantity x plus 1, all over x plus 1. Well, power to power is multiplication. So squared squared, 2 times 2 is 4. I noticed that this simplifies a little further. Notice we have one factor of x plus 1 in our numerator, and we have 4 of them down here in the denominator. So if we cancel the 1 in the numerator, that would leave us with 3 left in the denominator. So we find that the second derivative of f of x is equal to -4, all divided by x plus 1 quantity cubed. So we're looking at when is the double derivative equal to 0, and where is the double derivative undefined. Well, if you look at it, there's no value where it's ever equal to 0. If we set this equal to 0, again, if we're looking at a rational function when it's equal to 0, we're really not worried about the numerator. So x plus 1 quantity cubed, if we multiply that by both sides of our equation, we get 0 equals -4, which is false. So this never happens. There's no value of x which sets it equal to 0. Where is it undefined? Well, it's undefined when our denominator is 0. So it's undefined where x plus 1 quantity cubed equals 0. Well, if you solve for x here, we can get rid of that cubed by taking the cubed root of both sides of our equation. When you're doing an odd index, when you're looking at the root, we don't have to worry about putting the plus or minus in front. So this cube cancels, then with the cubed root, leaving you with just x plus 1. What do you cube to get 0? Well, that's just 0. So solving a linear function, x plus 1 equals 0, subtract 1, we get x is -1. Okay. So it's undefined here. It's actually undefined here too in our original. And I notice that it sets my denominator equal to 0 and not my numerator. So we talked about this at the beginning of the semester. This is going to be x equals -1 is going to be a vertical asymptote. So it's possible it's changing concavity on either side of that vertical asymptote. So we want to look at our number line, place the critical value we found where it's undefined is -1. And we want to test values on the left and the right by plugging it into the second derivative. If we choose a number smaller than -1, so maybe -2. And we plug it into the second derivative. Really, we're only worried, is it positive or negative? So my numerator is always going to be negative. If you take -2 plus 1, that's negative cubed is also negative. So negative divided by negative is positive. So this is greater than 0. So that tells me that it is concave up. So right now we have it's concave up from -infinity to -1. So now let's test on the other side of x equals -1. So maybe x equals 0. So if we go back into our original function, not original, our derivative, and we plug in 0 there. So numerator is always negative. All over 0 plus 1, that's 1 cubed, that's positive. So something that is negative in the numerator, positive in the denominator, that's equal to a negative number. So this is less than 0. So that tells me that it's concave down. So we just found it's concave down. From -1 to positive infinity. There is no inflection point because again, at x equals -1, it's not defined in our original equation. If it wasn't defined in our original equation, we'd go back in and plug it in that value of -1 into the original equation and find the y value, and that would give us our point. But in our case, there's no inflection point or points. You guys are frozen a little bit. So let me try to stop the recording. So I don't know if you guys can hear me or not. I'm just pulling up the task manager. Let's see. Okay, so I just kind of wanted to put the screen back up just because I had lost connection for a little bit, just to make sure that it got recorded. But we finished that problem. We found where it was concave up, concave down, and saw that there was no inflection point because there was a vertical asymptote there.